Okay, let's get started. Today we start familiarizing ourselves with the theory of dual spaces, which is a large topic, a complex topic, so I don't think we can cover all the aspects of dual spaces in a lecture. The rest of the book is mainly built on the theories of dual spaces, so we will have time to learn a lot about the duals. So in this lecture, which is supposed to be an introduction to the topic, we will quickly go over some fundamentals. Then we will we will solve a problem together. So first of all, what are dual spaces? If we have a linear vector space that we can call a primary space, there are linear functionals that are interpreted on this vector space. And in this case, we say these linear functionals are in the dual space of the primary space. Dual spaces are useful. They are important because we can use them for various purposes. For instance, and this is the most important aspect of the problem for us, we can use dual spaces to solve optimization problems. For instance, if we have a complex optimization problem in a vector space, it can be complex or difficult because for instance, it has infinite dimensions. We can simplify the problem and solve the problem, the same problem, in the dual space of the primary space. Or the other way around, if we realize that an optimization problem is defined in a dual space of a primary space, then we can solve the optimization problem in the primary space. The exercise we are going to solve in the second part of this lecture is an example of this type of problem. So we will see that the original problem is in a dual space, can be interpreted as described in a dual space. We will find its primary space, and we will solve the problem in the primary space. This is a very useful feature of dual spaces because dual spaces can help us solve many problems. So, if you browse chapter 5 of the textbook, you will realize that the theory of dual spaces is very complex and very difficult. The theories have geometric or interpretations sometimes, but not always. So sometimes it's instructive to imagine geometrically the theories, but sometimes we cannot do this. The chapter of the textbook on dual spaces is quite brief. And when going over, you might realize that that it's very theoretical. So even if the textbook contains a lot of groundwork on dual spaces, the reader might have no idea how to use these theories in solving actual problems. This is the reason why I thought it would make no sense to cover the complete chapter in a lecture, because you can do this. So you can read the chapter and you can understand the content, the basic message of the chapter with some work. But reading the chapter, learning the chapter, doesn't help you to learn how to use dual spaces in optimization. This is something we want to learn. So I devoted the larger part of this lecture to a complex problem to show you, to demonstrate how to translate a problem, a complex problem, into another problem defined in a dual space, or from the dual space into the primary space. Luenberger warns us that the remaining part of the book is based on the theory of dual spaces, so we will have time to learn the theories. So this is only a first step, and subsequent steps will follow as we work through the book. Okay, I devoted only one slide to the basics. First of all, let's try to understand the concept of linear functionals. A linear functional is a special kind of functions. While functions are interpreted on the real line, linear functionals are interpreted on more generally understood vector spaces. So in a vector space, we have points, and such points go into functionals as arguments. With a linear functional, or with linear functionals, we can characterize points in a vector space, because if we input a point as argument into a functional, then we receive a real number. Linearity understood in a very general way, so there is no surprise in this respect. But we must pay attention to bounded linear functionals. By boundedness, we mean that we have a linear functional, and the absolute value of the linear functional cannot be higher than a constant times the norms of any points in the vector space, and the smallest of such constants is the norm of the linear functional. This is important because we pay special attention to bounded linear functionals. If we have a normed linear vector space, then the bounded linear functionals on this space live in a space that we call the norm dual of the primary space, which is a Banach space. So the dual space, the norm dual, is a Banach space. You can see some the duals of some common vector spaces. I think it is interesting. So the dual of the Euclidean space, finite dimension Euclidean space, is the space itself. So linear functionals interpreted on points of the 2 or 3 dimension Euclidean space, they live in the same space. So actually they are points. It means that they are points. So we can calculate the inner products of points and points, because one of the points is a linear functional in the 2 or 3 dimension or finite dimension Euclidean space. We will use the fact in the third bullet point today that the dual space of L1 is L infinity, but not the other way around. We will use this fact in the upcoming exercise. And the exercise, most importantly, the exercise is built on corollary 1 of page 123. This is the theory we are going to use right away. You can see that we have a series of linear equalities. And this is the theoretical background by which we can change the problem. We are looking for a functional, a point in a space. This is x asterisk. This is a minimum norm problem, and we can change this problem into a maximum problem. Admittedly, this is very complicated in a slide, but this is the reason why I tried to put this theory and these concepts into action. So before wasting any time, let's turn to an exercise in which we will use these concepts and this theory. Let's do this.
Okay, let's have a look at problem 6 of chapter 5, which is a beautiful but complex control problem, by which I like to show you how to use dual spaces to simplify problems. So in cases where we have infinite dimension problems, we can use the duals to simplify the problems into finite dimension problems. This problem is about a rocket that we want to get to the International Space Station with given boundary conditions. We know that function xt describes velocity, and we have some boundary conditions. Initially, we are in a state of rest. So this is a set of initial conditions. We know that the second time differential of the velocity function is ut, which is the unknown control variable. So this is what we are looking for. And we also know that at the end of the mission, we must also be in a state of rest. So these are the terminal conditions. You might remember that in the extra exercise added to Hilbert spaces, to the lecture on Hilbert spaces, we tried to find restrictions on the control variable, the function, control function, on the basis of our boundary conditions. So this is what we are going to do. Let's use the fundamental theorem of calculus. What does it say? It says that if it is true, if it holds, then it also holds. Okay. So by applying the fundamental theorem of calculus, we can say the following. If the second time differential of the velocity function is ut, then the first time differential can be described in this way. Of course, there was something missing. Okay, yes, so here we go. And more specifically, it also holds. Okay, And now we can start using the boundary conditions. So first, at the end of the mission, we must be in a state of trance, not trance, rest. This is 0, and initially this is the other boundary condition with respect to the first differential, time differential of the velocity function. Between 0 and 0, note that the limits are both 0. So this must be 0, this part must be 0, and from this it follows that c, the constant, the unknown constant, is 1. And given this, the first condition takes the form that 1, so the constant is 1, plus the integral between 0 and t, us ds is 0. Okay, and this part must be -1. Okay, and now we can start going backwards to learn something about the velocity function. So it is going to be a double integral. So let's start with some work with the notations. This is just notation at this point. And from this, it follows, from the fundamental theorem of calculus, it follows that if we integrate the previous function between 0 and t, we receive the velocity at the end of the mission. So we have this integral. This is a freaking double integral. Actually, this is the sum of two integrals. And the first part is quite simple. So the first part only says that we integrate 1 with respect to tau between 0 and t. So this is t. That's all. So this is the first part. The second part is a freaking double integral. us ds d tau. And we might, so the idea is we should integrate it by parts. To do this, we must squeeze a new variable into the integrand without changing the value, so it's gonna be 1. Okay, and to familiarize you with the idea, this is the function, this is a function which is the differential of something in terms of tau, and this is a function. So, to expand this integral, then this is the function, the differential of which with respect to tau is 1, so this is tau, times the other function, and we take it between 0 and 10. T, sorry, minus and all this comes from the rules of the integration by parts. Note that this part is t times this integral okay, this is 0 and it is minus t because, as we have just seen, this is minus 1. The integral of u between 0 and t is minus 1. Okay, and we have the following. On this basis, we have the following. So we know that the velocity function at t must be 0, and on the basis of the integral we have just completed, this is a sum t minus t minus this integral, and this is 0. So it follows that this final part in the integral must also be 0. Hooray! So we have learned a lot about the unknown function u. And before moving on, let's summarize what we know. First, we have two kinds of restrictions on constraints. One set of the constraints comes from the physical properties of the problem. So we know that at the end of the mission, we must be in a state of rest. And another kind of restrictions comes from what we require the unknown function to be. And it cannot be higher than 1 in absolute value. So for any t between 0 and capital T, the function cannot be higher than 1. So we must realize, to move on, we must realize that this is a norm. This is a norm. Which is familiar to us. So this unknown function u is in this function space, because we realized that the norm we use belongs to this function space. Okay, so we know something important about the unknown function u, and given the fact that u can be anything, this is an infinite dimension problem. So the idea is that we might want to simplify the problem into a finite dimension problem if we think that U and its space is the dual of another space, function space, and instead of finding U in an infinite dimension problem, we might want to find another function in the dual in a space whose dual is L infinity. So this is the idea. This is one goal. Goal one: find U in this function space. And goal two: find the minimum time. Which we denote by T min. Okay, so the goal, goal two, in other words, means that we want to reach the International Space Station in the shortest time possible. But the time in which we can reach the International Space Station depends on U. Okay, so if we had a U that can be extremely high, then the time would be infinitely small, so it could be zero. So there is a trade-off between ut the absolute value of ut, and t min, the minimum time. If we want to reduce the necessary time, we will need high U functions. So if we had a small value for t, then our U, we cannot be sure that U will not be higher than 1. So if the minimum time is too small, then the norm of the function, the control variable, might be higher than 1, which is not good. So the strategy is the following. As the part of the problem, we want to find the minimum time. We will do this by choosing a sufficiently small t, and we will set up a set in which we collect those for a given t. We collect those ui functions that meet the requirements okay. And now we can check, as a second step, we check if this third restriction also holds. So we will check if with a given t, the functions the ui functions meet this particular requirement. if t is sufficiently small, then we will have no appropriate UI functions. By appropriate, I mean that functions that meet this requirement. So, this is a grouping process. So, we start with a sufficiently small t, with no appropriate UI functions, and we increase t in small steps until we find a function, increase t in small steps until we find a function whose norm is 1. Okay. This is all. This is the strategy. And let's follow this strategy and solve the problem. Okay, so the restrictions. We have 2 restrictions for the sake of good order. This is -1, and restriction 2, this integral is 0. Note that this is an infinite dimension problem because the concrete shape of ut is unrestricted, so it can take any shape. We know that this unknown function is in this function space. So we are looking for this function that meets the 2 restrictions. The inner product, so let's formalize these 2 restrictions with the use of the inner product of the function space. The inner product of the function space we work with is specified on page 48 of the textbook. This is simple. This is the inner product. In general, xt, yt, dt. So, accordingly, by applying this notation, restriction 1 can be rewritten in this form: ut dt -1. So, note that this is y1, and restriction 2 this is 0, and y2 is t. Okay, so the exercise is a minimum norm problem, so this is what we want to solve. With these restrictions. So for any given capital T, we are looking for the set of appropriate u functions, and we want to find the function in this set with the minimum norm, and we check if it is equal to 1. If it is equal to 1, then we are done. If not, we need to increase capital T a bit. So this is our strategy. So let's turn to corollary 1 on page 123, 124. So let's turn this minimum problem into maximum problem. We have this vector. This is C1, this is C2, right? So for the sake of good order, this is C1 and this is C2. And A, of course, A1, A2. And from this, C times A is minus A1. So the maximum problem, the analog maximum problem, is maximizing minus A1, supposing that the norm of this function is not higher than 1. What we use is that L infinity is the dual of L1. Okay. So this is the reason why here we are talking about the norm of the space, function space L1. So, in other words, we can also say that the problem is maximizing minus A1, supposing that the norm of this function is not higher than 1. What is YA? It is the product of two vectors. The vector of A1 and A2 and the vector of Y1 and Y2. And if we expand it, then we receive this function. So this is the way how we got here. Okay, before moving on, let's have a look at the physical properties of the problem. It's gonna be instructive. So let's try to draw a figure. This is T. This is the end of the mission. So let's try to imagine a velocity function. So what if velocity takes this form? We know that its time differential, in this case, this is the maximum of the speed, where its differential is 0. So we would have something like this. this is x dot at the end of the mission, which is not 0. Physically, it would mean that the rocket bumps into the International Space Station. So instead, we require something different. This is the end of the mission. And at the end, we require that velocity must be 0. So we must approach 0 very gently. So in this case, there is a point where the velocity function is the steepest, and its time differential would look something like this. This is s. Okay. And at time s, the time differential of the velocity function is the smallest. It looks good. There is an important thing that we know. Xt, velocity, is increasing first, then it's decreasing. So its time differential, it's not correct, to say the least, because this is the maximum. So it looks something like this. Okay, so x dot is positive in the beginning, but it turns into negative. Then it goes back to 0 because of this requirement. But we also know that ut must be aligned with a linear function, which means that the sign of the line drives the sign of ut. So ut is plus or minus k, depending on the line being negative or positive. So ut, which is the second time differential of the speed function, here until s is minus k, and here after s is k. So the appropriate figure so this is the maximum, where the speed velocity is the maximal. Okay, and this is time s. So something like this. We receive something like this. Yes, this is the maximum point of velocity. Xt. This is x dot, and on this section, okay, because it must be a line and another line. straight lines because its time differential must be constant. So this is what we know from the physical properties of the problem. Okay. So the rocket first reaches its maximum speed, maximum velocity, then it starts slowing down. So the time differential of velocity becomes negative, but then it grows back to zero. Okay. Okay. Okay, so what we know is straightforward. We are looking for a function ut which is x2 dot, the second time differential of the velocity function. Initially, between 0 and s, it is negative. When time is between 0 and s, then it is plus k when we are beyond point s. Okay, so let's use these facts. We are looking for two parameters. K and s. Okay. It also means that according to the norm of the function space, the norm is k because u is plus or minus k, so the norm is k. Okay, which cannot be higher than 1 by assumption. So let's use these facts. We know that minus 1, so this, okay, let's start backwards. Ut dt is minus 1, so let's halve the function. Between 0 and s, this is minus k, and between s and capital T, the end of the mission, this is k. And if we calculate this integral, we will receive that k is equal to 1 over 2s minus t. This is elementary calculus. So t is given. And k is a function of s. All right. This is requirement 1. Requirement 2. 0 is equal to the integral t times ut dt, and we integrate the functions for the two sections separately. This is not too complicated. So if we calculate this integral, we receive s equal to this number. And for any given t, s is determined. S is determined, and to this S from this, the previous equality, we always have K. So everything is going well. So we have two equations. And from this it follows that K is equal to 1 over square 2 t minus t, 1 over yes, and from this in a few steps it follows that kt is equal to this number. Okay. We know that k is equal to the norm of the unknown function u and cannot be higher than 1, so k cannot be higher than 1, and it means that t is higher than square root of 2 plus 1. Its minimum is when the inequality holds with equality. So we have the minimum time. And most importantly, k is 1. All right, so we know that ut is minus 1 when we are in the initial phase and plus 1 when we are in the second phase approaching the International Space Station. Okay. The strategy that we have followed so far was that the unknown function ut is aligned with a line a1 plus a2 t, so this function is a line. Okay, and this is a1. We know that initially it is negative and later it becomes positive because u was negative at first and it was positive in the second phase of the mission. So the function a1 plus a2t must be increasing. Let's turn this problem into another but equivalent form. This is t, this is s, and we are looking for a line that is 0 in time s, and its time differential is m. This function is minus ms plus mt because in s it is 0. minus ms plus ms is 0, and its time differential is m. Okay, so we are looking for m and s, and we want to check if we receive the same result as we worked out previously. So we are looking for a function, to sum up, we are looking for a function with which our unknown function u was aligned. We must find m and s so that the norm is not higher than 1. In other words, this integral is not higher than 1. So, the function is the absolute value that we want to integrate. This is t, this is s. So on the one hand, we have a triangle here. We have a triangle here. This is mt minus ms. This is minus ms for the sake of good order. Yes, and we have another triangle here. This is ms. And we want to find the area of these two triangles. Okay, the integral of the absolute value is simple. It's not too demanding. Okay, the sorry. No. No. So this is the integral. Okay, and it cannot be higher than 1. Okay, so to be clear, we have the same problem in two forms, two equivalent forms. The one is, let's maximize minus a1, supposing that this norm is not higher than 1, and it is the same as maximizing Sm, right? By requiring that this norm is not higher than 1. Minus a1 is a positive number, and Sm is another, an equivalent positive number, equal number. So, let's focus on this inequality. It means that by simple algebra, we receive this inequality. It cannot be higher than 1. So, from this it follows that yes, 2 over t squared minus 2. Yes, it's okay, it's correct. And from this, it also follows that this inequality holds. Note that on the left we have the expression that we want to maximize in terms of S and T. So this is what we want to maximize in terms of S and T, because this is all we have on the right. And it is easy to realize that its maximum is where the inequality holds with equality. So actually we want to maximize the expression on the left in terms of S and T on the right. And it's simple because what we need is to find an S as a first order condition, in a first order condition, by which we can express S as a function of T. By doing the math, we will receive this requirement, and it is 0, because we are looking for the maximum of Sm. So we differentiate the expression on the right with respect to S, and we express S as a function of T. So the maximum of Sm is where okay, this is something that we know. So let's put this expression into the maximum from which it follows that Sm is equal to this ratio. Interpretation. This is the maximum of Sm, which is the minimum of the original problem. So given that this is 1, then this equality holds, from which it follows that the time is the same as we calculated previously. So we solved the problem in 2 different ways.